Hello team, and welcome to another exciting episode of the video walkthroughs for Compiler's assignment for code generation. This one continues on the previous video guide, which showed the creation of a code generator. But the created code generator had bugs. That is, it produces assembly files that aren't correct, that don't do the right thing. So in this continuation video, we're going to talk about how to debug a code generator, because actually you may spend a significant fraction of your time running your candidate compiler through test cases over and over again to see if it's working correctly. So that's what we're going to get to here. All right. So in our last exciting episode, we had run our code generator, and then when we passed the resulting assembly through Cool, it says, oh, you're trying to read from a register that's never been assigned to, there isn't a backtrace, this seems really bad. And one of the first things I want to consider, there are two very important sections in the Cool reference manual about Cool assembly language. Indeed, one of the big reasons to use Cool assembly language instead of x86-64 is that it provides better debugging support. You're going to see that it's going to be fairly simple, I hope, for us to debug any of these code generator problems. And the first part that's worth paying attention to is addresses. All right? In order to allow you to tell the difference between code, heap allocated data, and stack allocated data, the reference Cool compiler, the Java virtual machine as it were, gives them all very, very different numbers. Right? So you can tell when you print something out, when you debug print something out, whether it was allocated in the heap or whether it lives on the stack, and that can be quite useful information. In addition, a bunch of useful features. The simulator tracks a notion of time. It will tell you when something was last written to. That's helpful in some obscure corner cases. But perhaps most notably, it tracks strings and labels and integer values separately. So if we try to debug, this is a special opcode provided by Cool that's not provided by x86-64 assembly. It will tell us not just the value, 3 million, but that value corresponds to, main.new, which is going to end up being quite helpful. All right, so let's take a look. It says on line 163, we're trying to read from a register RA that's never been assigned to. Where is that? 163. That's right at the beginning of start. So we've barely got anywhere, and the trick is that while push RA might be a very good start, very good beginning to a number of method calls like new main.main, for the actual bootstrapping start, maybe it's not such a good call. So what we're going to do is, we're already there. We're going to go back to the future, back to the end, all right, to the part where we're looking at start. And this is where we're pushing RA. And it looks a lot like we don't want to be doing that when the method name is start. So we rerun OCaml, and we rerun Cool. And now, this gets a little more interesting, we're attempting to read from a memory address that has never been written. And we can actually get quite a bit of information here already. We remember that big values like these correspond to, I believe, the stack. Let's just go double check. All right, addresses near 2 billion are the stack. All right, so we're trying to read from some, stack pointer that wasn't really there. Oh, and this is very interesting. Now the best effort backtrace tells us that we are in IO out int from line 175. From line 175. All right, well, let's go. All right, we know where out int lives. All right, so we're somewhere in here, and we're trying to, on line 108, read something invalid. Oh, well, that's a shame, because this instruction here, it's trying to read the contents field. All right, so this means that we're not able to get the contents, but the contents field should be in the heap. Right? We should be getting it from an integer object, so this doesn't make much sense. And indeed, this is the default state when you're dealing with a wayward code generator. Like, where did this junk come from? But we do have one other bit of information. There's a call to IO outint from line 175. Where was that? Oh, down here. Well, this doesn't make any sense at all, because in start, we're trying to call main, but we somehow ended up at io.outint. Well, let's just verify that. I'm going to add a debug statement. This is in cool asm only. All right, this is your benefit for using cool assembly language. And now when I rerun cool, this is what the debugging looks like. They all start with debug, so you can filter them out if you want. At time 79, that is even just going through this push and pop and whatever has taken 79 time units, register 2 holds io.outint. Huh. Well, that doesn't make a whole lot of sense, so let's figure out why. And I like to suggest that debugging is hypothesis testing. All right? Hypothesis 1 might be we read from the wrong index somehow. Hypothesis H2 might be we read from the wrong v-table somehow, right? Like we got it on this line, R2 bracket 2, so either the 2 was wrong or what was in register 2 was wrong. Well, one way to test that hypothesis would be to print out register 2 right here. We expect this to be like main.vtable. Let's see what it says. Oh, it says it was int.vtable. All right. So now we've been able to, we're pretty much in this world, hypothesis 2. We're reading from the wrong vtable somehow. All right. So why? Right. So we're getting this from register 1. We'd previously pushed it. We're calling main.new. Right? And main.new is supposed to return us something in the accumulator, right? Register 1. So to track this down, we're going to need to go into main.new. Right. Here's main.new in all its glory. Oh, FIXME, calling convention stuff. Ha! We forgot to fix up some of the calling convention stuff. Well, that's embarrassing, but that's probably also going to, help us get to the bottom of this. FIXME calling convention stuff. All right. So what we were trying to do here is call new f-type. But actually, there's a potentially easier way to do that. We could just call cgen of new f-type, because we filled out the calling convention stuff much earlier. Right? We did, pushing the frame pointer, popping the frame pointer. So rather than duplicating that code, right, where was that? FIXME calling convention stuff, right? We can just call new f-type. Now, when we want to generate code, we have to pass in a symbol table, but we just happen to know that to generate code for new f-type, you don't actually need to know any of the variables. So we'll just pass in sort of a null symbol table, and then we will now get the benefit of pushing the stack pointer and the frame pointer and all of that good stuff. All right. So now we rerun OCaml, and now we rerun cool. All right. But things are still not correct. Right? Assembler, attempt to read from memory address. Well, one of the things we're going to do is go back and once again debug R2 to see if we're getting main's vtable or IO's vtable. And we're still getting IO's vtable. That's very mysterious. I'll just leave that on the screen a little longer. We're still getting IO's vtable. So let's go see why. And we may need to look into new main, all right, in order to see this happen. So the frame pointer gets the stack pointer, we push the return address, all right? And what we're hoping to do at the end of the day, right? Here's one hypothesis, right? It's my hypothesis. The newly allocated object is getting lost somehow, right? We're scribbling over it because we're not smart, because we're not saving important values before using them, say. So again, we're going to do a little hypothesis testing systematically. All right, for main.new, here, we debug R0. This is the object we want to return. All right? So we're going to debug R0, and then somewhere down at the end of the day, right, this is what we are actually returning. So the check is, are they the same? All right. Oh, no. No, they're not. One is 20,000 and one is 20,040. Now, that's fairly interesting, but actually we can get a little more information about this based on how cool allocates numbers. Now, 20,000 we know. That's the first heap address, right? Memory locate, blah, blah, blah. Stack addresses. When memory is allocated by the alloc instruction, addresses starting from 20,000 are used. So 20,000 was probably the first object we ever made, right? That's good. That's new main, right? But, you know, what would 20,040 be? Did we really allocate 40 new objects in the interim? Well, if we keep looking, when dynamically allocating memory, the simulator actually allocates more space than is needed and leaves the remainder empty. For example, if you make 2 allocations of 5 words each, you may get the addresses, it may round up, and then the range remains unused. So these values, you know, 20,000, 20,040, that doesn't actually mean there were 40 separate allocations in the middle there. There may just have been 1 or even 0 between them. And the cool runtime system is spacing them out officially to help you notice stack over or buffer overflows, because if you access invalid memory, it yells at you immediately. So by putting space between objects, you can't really have big buffer overflows. But it also means that it's easier to keep track of allocation. Right? So probably we allocated some other object, maybe 2010, 2020, 2030. All right. But we lost it in the middle. All right. Well, there were 46 lines here. Let's just go through to like 23. Do we still have it? All right, well, I'm just going to bisecting search, delta debugging. Let's go see. No. Oh, very interesting. At this point, it's now 2020. And this does suggest, if we think about what's going on, remember that when we make new main, that's the first object, but then we make a default integer for A and a default integer for B. So it's almost certain, I mean, we really hope, but like we really think that this is the new main object, this is the first A, and this is the first B. And what's happening is somehow these fields are overwriting register R0. When we're making the fields, they're scribbling over register R0. Right? Well, one way to check that is when we're calling int new, I could just print out the accumulator. So now the hypothesis, when we make new integers, they are scribbling over R0, which is the retval of main.main. If this debug is the same as the later ones, then we gain confidence in this hypothesis. Right? So immediately after int.new, R1 is going to hold, you know, the value of this newly allocated integer. Yep. Aha. Right. So it's not exactly the same, but this starts to tell you how we got up to 40. Remember that we first make the new main, and then we make int 0, and then we make int 0, and then we have the 222, and then we have the 333. Well, these are 0, 0, 10, 20, 30, 40. right? But they all start with, right? So it seems likely that these are our 5 objects. All right. So then after the next time we do new int, I'll just do a debug down here. Like we'll make this hypothesis just a little bit lower the second time we allocate an integer field. Aha, and now we see that this 2020, this R1, right, it's at line 75. There are a lot of debugs, maybe it's hard to figure it out. This one's on line 75. The one we got back from int new is somehow ending up just 12 lines later overwriting R0. Well, one easy hypothesis is what's R0 right now? Like right now on line 75. Oh, it's already overwritten. We're already dead by this point. Well, what was it before int.new? Before int.new it was one of the, well, it was the previous integer value. We're starting to formulate a hypothesis. What about right up here on line 66, before the first call to int.new? It was correct. And then down here on line 68, it's incorrect. So we have narrowed down exactly the problem. Executing line 67 scribbles over R0. And now if we go back to think about it, so like now we know calling int new scribbles over R0. But yes, actually, they do it right here. This is not surprising. Our constructors are set up so that they make a new self object. Like that's the point of a constructor. So if we want the self object to be preserved across a call to constructors, we're going to have to store it somewhere safe. When we want to store something somewhere safe, we store it on the stack, right, in our stack machine. So let's just go down to where we were generating code for new. Right. Oh, we can't actually say that. There we go. If we want to preserve the value of self, then we must manually preserve it, right, before a call to new. Notice that it's self frame pointer, but frame pointer self because it's a stack. So now we rerun OCaml, line 179. You forgot a semicolon. You're right, OCaml. So now we can rerun cool. All right. So now we get a different error. Line 184, attempt to read from register R0 that's never been assigned to. Well, let's go back to our original hypothesis. What vtable are we executing here? I'd really love to see main vtable. Huh. Very interesting. Do we even get here? We don't see this at all. You see on line 184. Push register 0. All right. So this is very interesting. We just added this thing in. Like this push register 0 and this pop register 0, those are the new code we just coded up right now. However, at the beginning of start, there is no register 0. Normally this would be undefined, but the cool Java bytecode machine, the cool virtual machine, is kindly telling us, oh, you're trying to read from a value that's never been set. That's probably an error. Initially, that should be something like null. So as part of this bigger special case, we said if the method name wasn't start, do this. But what if it is start? Maybe if it is start, special case, self is null. Oh wait, this is, don't mind me. All right. And then similarly, we may want to, well, we may need to initialize some other things later, but for now, let's see about setting register 0 to null. We run OCaml, and now we run cool. Ah, all right, now look at this very closely. Here's a 333. The hope is that when we call outint on a plus b, we'd get 555. Looks like we're printing b plus 0. Conceptually, an easy way to do that would be they're both lined up on the stack and we're off by 1, or we're not storing them correctly. But this is a very good sign. We're like halfway there. But then after that, we get this other error, 197, attempt to read from. All right, 197. Oh, that's right at the end here. On our way out of start, we are loading the top of the stack to get the return address. But there is no return address to start. We just call, syscall exit after this. So if we maybe we can take this and put it here. All right. So now we are printing out something. It's just the wrong thing. Now, just to make me happy, previously we were never actually calling the right symbol table, or the right vtable, sorry. We weren't calling the right vtable. Let's go see what it says now. Oh, now we are calling main vtable. Oh, that's great. Are we actually going to main? Oh yeah, we're going to main.main. Oh, that's great too. All right, so we are going to the right place. So now we just want to check in main.main. Here's where we're generating the code for a.b. Right? And this part here, this is where we're getting the contents fields. These are the two numbers we're trying to add together, right? Because right after this, we do the add. So what are they? Well, we think there's 0 and 333, and then we add those together and get 333. Well, at least the add works. All right. So this gives us a little bit of information. What was supposed to be in register 1? All right. When we were generating code for a plus b, and you check the cool reference manual or whatnot to see if this was correct, first generated code for a, and then we got it from one of these fields, and then we pushed that on the stack, and then we generated code for b. So now this R2 holds a, and R1 holds b. So when we're printing these out, we think that B is the first one and A is the second. Like, that's what the compiler is generating. So we think B is 0 and A is 333. We are way off. All right. So why do we think that? Well, when were those values set? They were set in main's initializer, main's constructor, main.new. Right? The A field of main gets a default int, the B field of main gets a default int. And then at some point, we are storing main's B field, main's A field initialized. Here's the 222 and the 333. So are these getting there? Well, when we were trying to get these, right, we thought this held B. Right, so right before we return, right, we can put these in some unused register to see them. So what I'm doing here, the hypothesis is something in the main new constructor is wonky, and we aren't leaving the constructor with the right field values, right? We want 222 and we want 333, but what are we actually seeing? We're actually seeing, of course, we're actually seeing pointers to heap values. So if I want to get the actual contents out, so I want to get out the contents field and print that instead. All right, so here we are seeing that A is 333 and B is 0 in terms of raw unboxed integers at the end of the constructor. So we've gained confidence in this hypothesis. We think this is the correct story. This is what's happening. All right, so why? Once again, one of the things we might do is go find a time, like here's one of the times when we're trying to put in this 222 and just sort of look at it and see how long it lasts. So here's where we loaded the immediate value 222 and we stored this in register 1 bracket 1. This was the integer. And then this is the like new boxed 222 int. And here's mains A initialized. Right? So one of the things we might do right now is just copy this debugging right up to here. Like hopefully this will say 222. All right, this one says 222. So when does it stop saying 222? Well, we push R0, we push the frame pointer, we call int new, we pop the frame pointer, we pop R0. All right, looks like we're saving a bunch of stuff. We load the immediate value of R2 333. So this is a new boxed 333 int. And then, oh, can you spot it? The error is on this line. This 1 shouldn't be a 1. A lives at slot 1. B lives in slot 2. So let's go back to our code. And when we were making constructors, somewhere along the way, this was laying them out by default. We set the index to 1, so it's 1 at the beginning. But if you look carefully, we never, whoops, we forgot to update that. So what was happening was we were generating code for every initializer and overwriting the first field with every initialized value. All right, but now when we increment the index, hopefully this will be a little better. All right, so we rerun OCaml, and now we rerun cool. Oh, and now we print out 555. All right. So, I mean, that seems pretty good. Let's be dangerous. Just to double check, we should get the same answer if we conceptually change the source code to be B plus A. Regenerate it and rerun cool, 555. How about if we do B plus B? We should get 666. How about if we do A plus A? We should get 4 plus 4. That seems pretty good. How about if we do A plus B. I will never, there is no hope. We completed the plus, we close that, close that. How about A plus B? That should be 777. 777. All right. So we feel fairly confident that we are generating decent stack machine code for programs with initializers. There is a what if, right? One of the things you might want to test on your own. Suppose instead this is something like 111 plus A. Right? You're allowed to do this in cool when you do the previous initializers can refer to the current ones, that sort of thing. You may want to check this out and make sure that the code is correct. But this is the basic plan. You would just go on and add more and more test cases, but that's tedious to do because I didn't actually bother to write a parser. But I want to just reiterate 2 or 3 important bits about cool assembly debugging. I encourage you to think carefully, right, or remember what these different values mean. This is a pointer to the code, right? This is a pointer in the heap, and this is a pointer in the stack. And also make heavy use of the debug opcode because it prints out symbolic values. And also remember that when you call alloc, it will space them out for you automatically so you can expect sort of round numbers. Well, that was much less painful than I anticipated in terms of debugging, but hopefully we were still able to go over some good points. If you've stuck with us for this long, hopefully you have a reasonable start on your own code generator. Good luck.